So the Dr. Papaioannou, he's a postdoc researcher at the KTH Institute of the Technology in Sweden within the ECO2 Vehicle Design Center. His research is including the motion comfort in the vehicle, human perception, the vehicle dynamics and control and motion planning. Uh, Today, his topic uh, is revisiting the design of the automated vehicles for enhancing motion comfort. So, so please go to your presentation.
Yes.
Would you like to share the presentation by yourself, or I
I
do
will
this?
I will share my screen.
Okay,
You,
Can you see
thank
it?
you.
oh
Yeah,
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 yeah.
it works.
So, hello, thanks, Helen, for the introduction. Hello, everyone, as well. I'm sorry that I'm not there. It would be much better, I think, but I hope I can transfer you my research through online. So, allow me to say first few things about myself. I did my PhD on mechanical engineering at the National Technical University of Athens, where I also did my PhD studies on enhancing ride comfort through suspensions and seat designs. Then I moved for my first postdoctoral experience at Cranfield University, where I focus on the fundamentals of motion planning of automated vehicles for mitigating motion sickness and also sorting the alternatives provided by the motion planner. Nowadays, I'm working at KTH, where I'm leading a project on energy efficiency, and at the same time, I work on motion comfort through vehicle and seat suspensions in order to enhance motion comfort in overall. Now, I'm moving at the U Delft as an assistant professor on predicting motion comfort in AVs within the intelligent vehicles group and the human factors team that exists there. Also, my topic today is about motion comfort in AVs, and allow me to say some things to introduce the topic. Motion sickness results. Motion comfort is the term that we use in order to combine motion sickness effects and ride discomfort effects. Motion sickness results from provocative motion frequencies that occur in a road vehicle in transit, and ride comfort refers to the vibrations that are induced to the human body by the road irregularities. Regarding the latter, its assessment is widely discussed and is based on ISO 2631, which fully covers the assessment and the analysis regarding discomfort. On the other hand, motion sickness is much more complicated since multiple factors affect it. The most representative maps of the factors that affect motion sickness is the one that you can see on this slide. The symptoms of motion sickness are affected by the sensory conflicts in the visual, vestibular, and the somatosensory systems, which are affected by the motion environment, by the motion that excite them, and also that the environment that the motions take place. And then we have the situational and the dispositional susceptibility of the occupants that also affect these sensory conflicts. The problem is that the current models in the literature right now don't consider most of these factors, apart from some efforts from, as we saw from Hailung before, and also Professor Wada, which consider the visual system and the sensory conflicts. But we don't have models that consider the situational susceptibility, as one of the hosts asked about the age and also some personal characteristics. But the question is why it is so important to be able to understand motion comfort. The ability to engage in other activities during being driven is considered one of the main reasons for the acceptance of AV's technologies. On the other hand, motion comfort is one of the main inhibitors regarding the use of AVs and one of the reasons that people will not accept them. And this is together with the cybersecurity, the safety, the personal and other reasons. So it's not only crucial to find ways to enhance it, where my research focus has been so far, but also to measure it, model it, and predict it, which is my research vision for my future position. So far, as I said, my focus was on motion comfort enhancement, and this is where I have been working the last years on building, finding ways through motion planning, chassis design, and seat design in order to enhance it through collaboration with different partners and colleagues. So I will start first with chassis design, and I'm always adding some of the papers that I have included, the material, the papers from where I have included the materials. Regarding chassis design, the idea that the driver is out of the loop now allows us to consider novel suspensions that we couldn't use in the human-driven vehicles. For example, we can consider the flat braking or the curve tilting in road vehicles, because we don't have the driver to need to send them the appropriate cues. But in order to introduce these novel suspensions, we need to know how motion comfort affects. So in this context, we built this paper where we had two main goals. The first goal was to fit a human body model into the perception models that exist right now in the literature in order to assess motion comfort based on the head dynamics. And the next goal was to investigate how the translational and rotational accelerations changed compared to the motion sickness incident in different chassis design configurations, different seating conditions, and also different road profiles. So regarding the first step, what we did, we built a human body model that consists of six transfer functions that exist in the literature, and they are extracted from experimental data. The first two blocks consider the transferring the vertical, the yaw, the longitudinal, and the lateral vibrations in the seat surface to the occupant's head, while the last two, the roll and the pitch, not only transfer the roll movements and the pitch movements from the head to the pitch, but they also consider the effect of other accelerations to the head. For example, how the pitch vibration is generating longitudinal accelerations to the head. And in this way, we are able to take these inputs, these outputs, the head outputs, in order to excite the perceptual models as Professor Wada showed before, the one that Professor Wada has developed. And in this way, we're able to evaluate the symptoms and intensity of motion sickness. So in order to evaluate to evaluate the impact of the translational accelerations to the motion sickness incident and the rotational accelerations, what we did was we optimized the vehicle suspensions for comfort and road holding in a very simple vehicle model while it is driven in Class B and Class C road roughness. In this way, we conducted, in this method, technically we had a multi-objective optimization, which provided us a set of alternatives for each road profile. So we had a set of 30 suspension systems for different road profiles. And then what we did is we conducted we simulated all the optimal solutions that we extracted from the optimization in IPG CarMaker in order to consider, while we consider also an artificial countryside road, in order to excite the three-dimensional responses. And finally, having the three-dimensional responses from IPG CarMaker, we assess the contribution of each translational or rotational acceleration to the overall comfort, and we evaluated the overall motion sickness incident then according to the updated 6DOF subjective vertical conflict model. The conclusions that we extracted from this work was very important, and more specifically that the seat-to-head transmissibility is a crucial part of assessing motion comfort. Also that the head rotation matters, and we need to consider the seat-to-head transmissibility. And different road profiles and different seating conditions didn't affect the importance of the head rotation. And also finally that the isometric cannot accommodate motion sickness reduction in suspension systems, and the pitch rotations should be included in the analysis, in the optimization, or in the assessment in overall. Now, the next part of my work the last years regarding enhancing motion comfort is on seat design, and I have attached a few papers on that. The seat designs, AVs are going to experience a completely interior redesign. The interior is transforming in order to be a living room or an office and accommodate the engagement in non-driving activities. And these help us to be able to add more larger seats within the vehicle's interior in order to consider as well seat suspensions there. In this direction, this year we designed two different seat designs, focusing on the vertical isolation and also multiple degree of freedom isolation systems. But let me show a bit about the first design. The idea for the vertical isolation is that when we have a high quality vehicle suspension, or our vehicle drives in smooth roads or in highway roads, then the dynamic seat factors are less important and maybe we don't need suspension systems in the seats. However, when the vehicle lacks of a good suspension or the suspensions cannot be optimized towards comfort, then we need to have good seat suspensions to isolate the vertical vibrations. And in this direction, we considered this year the active case seat, a model that is working based on case seat and novel seat suspension that I developed during my PhD, which has negative stiffness elements in order to decrease the dynamic stiffness of the suspension and provide much better isolation. And the case seat has been proven one of the most effective in seat comfort at that point, and it was adaptable in different occupant masses and efficient in different road profiles, and also very good in isolating low frequency vibrations. And this is very important because motion sickness occur in low frequency vibrations. The next seat model that we considered is a multi-DOF isolation system, because in this way, with such seat suspensions, we are able to complement the flat braking or rolling inwards the corner. So instead of having maybe a vehicle is not able to lean towards the curve, so maybe there is the need from the seat suspension to support further. So that's what the design concept that we implemented is. We designed, as I said, an integrated seat design that isolates both the vertical and the longitudinal isolation. It consists of a parallelogram frame, a rotary motor, and a torsional spring in order to guide the seat and translate the Z and X motions to rotary. And here we use two PID controllers to provide the appropriate torque for minimizing the longitudinal and the vertical accelerations. In order to extract the results, just simply show you the methodology, what we conducted. We simulated in IPG CarMaker a vehicle driving a real road path with Class B road roughness. Then we excited many different seat suspensions that exist in the literature, very novel suspensions, including a passive, a simple passive. And finally, we assessed motion comfort based on ISO 2631 and also motion sickness incident based on the 6DOF subjective vertical conflict model, considering as well the human body dynamics that I showed you before. The conclusions that we extracted is, first of all, the active case seat can significantly improve motion comfort, decreasing the shaking frequencies also. And this is very important because this means that maybe in the future, with seat suspensions, we will be able to enhance the performance in engagement of non-driving tasks. And finally, that the multi-DOF isolation systems illustrate great potential in decreasing motion sickness incident compared to all the rest of the designs, illustrating a 30% decrease of the motion sickness incident. Finally, the last part of my presentation is about the motion planning and enhancing motion comfort through there. As we said, the driver is out of the loop. We have this paradigm shift from the role of humans as driver to the role of passengers in autonomous cars. And this allows us to completely re-examine path tracking approaches in order to get more comfort-oriented driving for the occupants. And this direction, some of our works was to investigate the fundamentals of motion planning, try to investigate the path tracking algorithms, and also finally sort the alternatives. So in order to do that, in order to extract these important conclusions, we formulated an optimal control problem for different time scenarios. we employed a simple one-point mass model in order to represent the vehicle dynamics, and we designed a multi-optimization problem for motion sickness and journey time, but turning it in a single objective problem with the weighted sum method by using normalized weightings, because the problem here is that we cannot focus on motion sickness minimization, because if we have only motion sickness as our objective, then the vehicle is not going to move, because the optimum is to not have velocity at all. So that's why we need to combine time and motion sickness as well. And finally, we added some inequality constraints in order to enhance the feasibility of the solutions. And more specifically, we used constraints to enhance vehicle stability and road holding, and also constraints to have to consider the lateral maneuverability of the road and the road borders. And this is important because in different countries we have different road borders, and the automated vehicle should be designed to be able to follow all of these scenarios. And in order to assess the different things that I will present later, we consider a long path, a 12-kilometer length, which includes sharp turns, U-turns, and we wanted to provoke motion sickness to the occupants through this detailed path. So the conclusions here was that indeed motion planning can be utilized to improve motion comfort, and in this way, in the method that we conducted, we assessed the levels of the compromise between time and constant velocity, how much we need to increase time in order to feel more motion sickness. The next conclusion is that the lateral maneuverability impact on illness rating differs regarding the path distance. When we have a long path, then the lateral maneuverability is not that important. So we can drive on the center line of our path, and this is crucial for the future connected and automated vehicles. While on the other hand, when we have small distance paths, then it plays an important role. And finally, the paths are very feasible to be tracked by simple path tracking algorithms, and this study was mainly conducted in order to illustrate the feasibility of the paths and see that these results can be utilized with simple control algorithms in an automated vehicle. So thank you all for your attention. I'm glad to answer any questions that have popped up, and I hope I gave you a good overview regarding the enhancing motion comfort by revisiting automated vehicles design. Thank you.
Okay, thank you very much. At the first, how could you turn on the mic?
Okay.
Okay, thank you. Thank you for your presentation. So, do everyone have some question?
Yes, I am. I have one.
Yes, please.
Georgios, thank you very much for your your presentation. So, I'm interested in the seat optimization. So, my question is, if my understanding is correct, so you introduced the human body model in your research, right? So my question is, how did you deal with the interaction between the human postural control strategy with vehicle motion? I mean, if the vehicle motion is changed, human, of course, will change the vehicle control. Control change. Is changed. So how did you deal with this kind of interaction?
The human models that we considered is built based on transfer functions that are extracted from experimental data. So technically, they consider they're evaluated based on the postural control based on the frequency that they are excited. So unfortunately, the model is very simple, so we couldn't see how the postural control changed based on the vehicle motions. So it wasn't a dynamic model that the postural control aspect was changing based on the vehicle motions or the seat dynamics. So it was just some experimental transfer functions that were transferring seat vibrations based on the frequency of the excitations to the head. But your question is very, very interesting, and this is very important to be able to know in the future to predict the posture of the occupant with regards to the vehicle motions and also the desired motion, what the occupant wants to do, or the occupant want to write on the laptop or take the mobile phone and write a message. These are very important because these affect motion sickness. Thanks for the
Thank you very
question.
much.
Okay, thanks. So, any questions? Yeah, please.
I have a question.
Yeah.
So, in your simulation, I don't know if you have also simulate or investigate the effect of the active seat suspension are more beneficial than the motion planning, which is focused on the minimize the motion sickness, or which of the system could be more beneficial? Because there is other systems also exist for active suspension. I don't know, lot of methods. So which one is the best method in your opinion?
From my experience, the concept is based on from the figure that I had in one of my slides. It's not one solution; is all together. You cannot focus on motion planning without considering active suspensions. And then, if you have designed these, maybe these are not enough, so you need seat suspensions. So the first plan is you need an algorithm to be able to calculate the motion. So you need motion planning. But if the motion planner requests, let's say, an abrupt braking for some reasons, then maybe you need active suspensions in order to have a flat braking or to counter pitch your vehicle in order to decrease the pitch motions and also decrease motion sickness. So, but then this pitch might not be enough, or the suspension systems cannot provide this counter pitch, and then the seat comes, and the seat can do this additionally. So all these solutions, they are not solutions that can work standalone. They need to complement each other and be a circle to follow what we have, what we need to add, and if we want to go further.
Most costly option, you say.
Indeed, that's true, but this is how it works if we want to do it. We start with motion planning, it's the first option, then we add up the suspensions, and if we need further, we add the seats. Automated vehicles are costly on their own. I mean, we are building cameras, we expect the cost of them to be huge, so at least let's make them comfortable.
Thank you, Georgios.
Yeah, thanks.
Okay. I have just one very short question. That is, you propose a method to control the seat or control the vehicle to reduce the motion sickness for someone have it, right? But for example, for someone, if this guy don't have the motion sickness, but you still use the to control the vehicle to make some motion, it gives some real motion information to that guy. Maybe they will have some motion sickness. So do you have any comment or?
So your question is that if, for example, the suspensions provide motion to the occupant that was not expected, and this motion can generate further motion sickness, correct?
Yes.
So this can only happen, I think, from the seat suspensions, but also the seat suspensions are controlled based on the excitations to decrease the motion. So it's difficult to generate further motions.
Yes, I
If
see.
I understood correctly. So we control them in order to decrease the longitudinal accelerations or the vertical vibrations. So we try to decrease the motions as much as possible in order to decrease the motion sickness as well.
Okay, thank you.